Finally, let's discuss now order relations. So let's see. The binary relation R subset of A cross A is called an order relation if it's reflexive, antisymmetric, and transitive. So everything we write here are considered to be universally quantified. First of all, reflective X R X, and for every X. Then antisymmetric X R Y and Y R X implies X R X equals to Y. So reflexive, antisymmetric, and transitive. X R Y and Y R Z implies X R Z. So these are the order axioms. Okay, so every order set, an order set is a set together with an order relation on that set. So order relation was the constant order relation was created just to model the regular order relation among the real numbers. So less nor equal is a common sense order. Think about order among real numbers, right? Among real numbers. That's how those axioms were modeled about the intuitive constant order among real numbers. So these are the axioms of order. So the real numbers together with the usual less than or equal is an order set. So that means reflexive X less than or equal to X, that's obvious. Antisymmetric X less than or equal to Y and Y less than or equal to X. If they are related both ways, then the only possibility is X equals to Y. So then X equals to Y. And finally, if X less than or equal to Y and Y less than or equal to Z, then X less than or equal to Z. So that's one standard example of order set. But it is so special that in the sense that not every set endowed with an order relation is similar to real numbers with the usual order. So there are also some very different order types. Let's give an example. Let's example 1, real numbers, with a common sense order. Example 2. Out of example 2, to learn some lessons and to see, to imagine order relations are not as common. So let's define D sub n for n a positive integer, set of all the numbers b bigger than or equal to 1, such that b divides n. So in other words, all positive divisors of n. All positive divisors of n, where n is itself a positive number. For example, d sub 1 is the set consist of 1 only. D sub 6 is the set consist of 1, 2, 3, and 6. All positive divisors of 6. So, but among the elements in D6, we can introduce a different type of order. Namely, two elements are related if one of them, the left one divides the right one. So X divides Y. That's the relation. So that's the relation is, this would be an order relation on Dn in general. Divisibility is an order relation on Dn. So, but this order relation is very different from the usual order relation among the real numbers. Why? Because we can find, look at this D6. We can find two elements in D6, namely 2 and 3, which are not comparable according to the divisibility order. So 2 and 3 not comparable. That means 2 is not a divisor of 3, 2 does not divide 3, and 3 does not divide 2. So 2 and 3 are not comparable. So therefore, we have to kind of adapt the naming of the ordered set, and the sort of ordered set is better that from now on we use poset, as in partially ordered set. So the order relation divisibility on the set D6 is not a total order, in the sense that not every two elements in D6 are comparable. For example, 2 and 3. Therefore, in general, we'll define the general concept of poset. So let me start from scratch here. Poset is acronym for partially ordered set. A poset is a set X endowed with the order relation of A. Again, satisfy the order axioms. X less than equal to X, X less than equal to Y, and Y less than equal to X implies X equals to Y, and X less than equal to Y and Y less than equal to Z implies X less than equal to Z. So in other words, a poset, okay, is any model of those axioms. So a poset model of order axioms, which are those reflexive, antisymmetric, and transitive. But the order axiom, so what does it mean? In addition to the order axiom, so we have an additional axiom which is not does not follow from the order axioms. There's a total order axiom. Is for every X and every Y, either X less than equal to Y or Y less than equal to X. So let's call this phi, the order axiom. The thing is, like we discussed so far, so basically it's enough, our previous discussion, to show that the order axioms do not have phi as a consequence. Why? Because not every poset is totally ordered. Not every poset, as in partially ordered set, is totally ordered. So if not every poset is totally ordered, like we give this example, D6 and divisibility, so this is an interpretation of the order relation less or equal. It's interpretation in this context, interpretation of less or equal in this model. So in this model, less than reads how? So that less than in this interpretation reads divisor of. So there's a model. A model is an interpretation of the axioms. So in this poset, all positive divisor of 6 with the order divisibility, well, this vertical bar, this symbol is means divisibility, and that's an interpretation of order relation. In this interpretation, less than means divisor of. How to obviously the order axiom, there's a model of the order axioms. Every number divides itself, right? Of course, if X divides Y and Y divides X, so then X must be equal to Y. And further, if x divides y and y divides z, then x divides z. So all three order axioms are obviously satisfied in this interpretation. But in this interpretation, the total order is not axiom is not satisfied. So because we can give a counter example, 2 not divides 3 and 3 does not divide 2. Okay, so this kind of example broadens our understanding of the order relation. So not every order is a total order, and we have to always take into account this fact. So, but just to be on the safe side, we call this structure, consisting of a set and a partial order relation on the set X or poset. And from context to context, it can have different interpretations. So here's another interpretation. Let's see, A could be the set 1, 2, 3. Let's define the following set X is a power set of A. Power set of A is a set of all subsets of A. So empty set, set consisting of 1, set consisting of 2, set consisting of 3, set consisting of 1, 2, set consisting of 1, 3, set consisting of 2 and 3, and set subset consisting of 1, 2, 3. So this is a power set of A. So on X, on the set X, define less than or equal. So we have to give, for the abstract axiom of order, we have to specify an interpretation in this context. So two subsets are related. So X and Y are not X. Let's see. So U and V are subsets of elements of X, means subset of A. So U and V, if U and V belongs to X, U less than or equal to V if U is a subset of V. So being related means being a subset. So in this context, in this interpretation, less than reads subset of. For example, 3 is less than to 3 because the subset 3 is a subset of the subset 2, 3, right? But the subset consisting of 2 and the subset consisting of 3 are not comparable. So 2 and 3, 2 and 3 are not comparable. In the sense that 2 is not the subset consisting of 2 is not a subset of the subset consisting of 3, and the subset consisting of 3 only is not a subset of the subset consisting of 2. So the subsets consisting of 2 only and 3 only are not comparable under the order relation inclusion among the subsets of the set 1, 2, 3. So again, we have a lot of examples of order sets which are not total orders. So that means that's why commonly use the term poset, as in partially ordered set. But like in the case of relations, we just got those conceptual diagrams which ease the understanding of the concepts. So in this case, for order relations, again, we have some diagrams which ease the understanding of order relations. These are the Hasse diagrams. So let's discuss Hasse diagrams for a while. So let's assume I have a set X with a partial order relation on X. It's a poset. Let's imagine x is finite just to ease the graphical representation. Right? So the main features of Hasse diagrams, to this poset we assign a Hasse diagram. They are very good tools in the conceptual understanding of the order relations. So two main ideas are here. If x is strictly less than y, if in the diagram we can climb from x to y continuously. From x to y, this is x, imagine this is x, this is y. So in the diagram, we can climb from x to y in the diagram continuously. So we can continuously climb from x to y in the diagram. So it's not like from x from x to y by going a little bit up, a little bit down, a little bit up. No, so this is not good. So we can climb from x to y continuously in the diagram. Okay? That's the first thing. And second thing, which is important to keep in mind, no unnecessary edges in the diagram. For example, if we have something like this, from A to B and B to C in a diagram, we don't put this one. It's an unnecessary edge because it's not enough to, it will be enough from this diagram because it follows that A less than C, because I can continuously climb the diagram from A to C and I also incorporate B in the process. So no unnecessary edges, and the definition of the order x is strictly less than y. So think about elements are not equal. If they are equal, they are equal. But if they are not equal, x less than y, if I can continuously climb in a diagram from x to y. Now let's give some examples. We discussed previously about D6 with divisibility. So order means divisibility in this context. So example 1. D6 with divisibility. There's the poset in this case. So D6 is 1, 2, 3, 6. The Hasse diagram usually is built from the bottom and by covering with minimal elements which are greater than the previous one. At the bottom of the food chain, so to say, is 1 here. Immediately bigger than 1 in the poset D6. Let me write again here. The poset consists of 1, 2, 3, 6. With divisibility is the order. Two elements are related if x divides y. So x are y if x divides y. So x less than or equal to y in this interpretation if x divides y. So which elements are minimal covers of 1? So which are bigger than 1, but not just minimally bigger. Well, they are the prime numbers. Minimal multiples of 1 are prime numbers. 2 and 3. Now, let's move on. What's the minimal cover of 2 and 3? So that would be a 6. This is the Hasse diagram of the poset D6 with divisibility. So in this case, 1 is less than 6 because I can climb in the diagram moving perpetually up from 1 to 6, which means 1 is less than or equal to 6. In this interpretation, 1 is a divisor of 6. Also, I can climb from 2 to 6, right? Only one step. 2 divides 6. So 2 is less than or equal to 6, but less than or equal, the interpretation is divisibility in this context. Also, 2 and 3 are not comparable. It's immediate when you see the Hasse diagram, which are elements are not comparable. 2 and 3 are not comparable. I can get from 2 to 3, but I cannot get from 2 to 3 by continuously climbing, neither from 3 to 2 by continuously climbing. So 2 is not less than or equal to 3, and 3 is not less than or equal to 2 under this divisibility relation. Oh, let's see another one. Example 2. What about D8? Let's look at the difference. Which are divisor of 8. D8 is divisibility. It should be the poset 1, 2, 4, 8 with divisibility. So less than equal, to be less than equal means divisor of in this context. So what's the Hasse diagram? Again, come to the bottom. Now let's do minimally bigger than 1. Bigger than is multiple of. So minimal multiple of 1, I don't have to move too fast. Minimal multiple of 1 is 2. Minimal multiple of 2 is 4. Minimal multiple of 4 is 8. So that's a nice Hasse diagram for the set D8. Look at the difference. So here is clear, we look at the diagram, and 2 and 3 are not comparable, but here any two elements are comparable. So this is a total order example. It's a nice image coming with the concept of total order by just looking at the example. That's why in total order in many books is called linear order, because the Hasse diagram is just a straight vertical line. So total order is the same with linear order. Okay, so in this case, D6 is the Hasse diagram is not a line like in the case of D8, especially because we got two numbers, 2 and 3, which are not comparable. 2 does not divide 3, and 3 does not divide 2. Whereas in this case, no matter which number we pick, one of them divides the other. So this is a natural question which arises next. For which numbers n, the divisibility relation on Dn is the total order. Let's see, let's have this question. Which numbers n greater or equal to 1 is Dn with divisibility a totally ordered set? Okay, so let's try to give an idea. So our example so far was 8. So what's so special about 8? 8 is a power of 2. 8 is a power of 2. 8 is 2 to the power 3. At the same time, 6 was not totally ordered, and 6 is not a power of 2. And for that matter, 6 is not a power of any prime. But 8 was a power of 2. For the same reason, instead of D8, I could have said D sub 3 to the power 4, right? Or 3 to the power 3, right? So with divisibility. So is there any difference between the Hasse diagram of D sub 3 to the power 3 with divisibility and D sub 2 to the power 3 with divisibility? No, because D sub 2 to the power 3 has 1, 2, 4, 8, and D sub 3 to the power 3 has 1, 3, 9, 27. Here are totally isomorphic Hasse diagrams. Only the notation on the vertices are different, but this doesn't really matter because these are the same poset here. So it's clear now that for every power of a prime, d sub d to the power k, the divisibility is a totally ordered set. So not only d sub 2 to the power 3, d sub 2 to the power n, d sub 3 to the power n, d sub 5 to the power n, the set of divisors of any prime power is a totally ordered set under divisibility. So d sub 3 to the power k divisibility is a totally ordered set. On the other hand, if n is not a prime power, then d sub n divisibility is not a total order. If n is not a prime power, d sub n divisibility is not totally ordered. How to prove this? Totally ordered. Okay, let's keep this statement here and then prove it. I'm going to have space on this board. put it here. Proof. So let's say n is not a prime power. So that means it has at least, it doesn't have only one prime in it. It has at least two prime divisors. So then n is at least two prime divisors. P not equal to Q. So we got P divides N, Q divides N, yet P not equal to Q. Like in the previous example, 2 divides 6 and 3 divides 6, yet 2 not equal to 3. Right. So P and Q, they belong to G sub N, are divisors of N. Yet P does not divide Q and Q does not divide P. So they are not related. So in no way. So P, because P and Q are different prime numbers, they cannot divide, none of them divides the other. So we just proved that N must be a prime power, because if it has two primes in it, then those two prime elements of the N are not comparable. Another example. What about the previous example used with subsets? So let's see another example too. The power set of a set A, so all subsets of A with the order relation is the inclusion. That's another example of an ordered set. The set is the power set of a set A, so all subsets of A. And the order relation is the inclusion. So what's the condition on A for this inclusion relation among the subsets of A to be a total order? So what is the condition of A such that the inclusion relation is the total order on the power set of A? It's something somewhat similar to the previous exercise. First of all, if A, let's say this is A, right? It has a lot of subsets, right? So the problem is it true that any two subsets are comparable under the inclusion? Means being comparable means let me show you exactly the image here. Being comparable means one of them is a subset of the other. So if there are any two subsets, one of them is included in the other. In this context, being less than is being a subset of. So less than in this context is the same with subset of. Okay, so clearly, if A has at least two elements, we can artificially construct the subset consisting of this element and the subset consisting of this element. Among these two subsets, none of them is included in the other. But they are different. So the subset consisting of one element cannot be included in a subset consisting of a different element. So if A has at least two elements in it, then this is not a total order. The inclusion is not a total order among the subsets of A, if A has more than two or more elements. Therefore, the condition, A must have one element. And if A has one element, A has, let's see, one element star, right? What's the power set of A? Is the empty set, and the full set is set consisting of star. And this is a clearly totally ordered, which has a diagram at the bottom of the empty set, at the top with the subset consisting of the full set consisting of star, right? This element star. So Hasse diagram is linear, which makes a total order. So the answer to this question is the inclusion on the power set of A is a total order if and only if A has one element. Or empty, or zero elements. The power set of the empty set is a set consisting of the empty set. So in this case, it's still a total order because we have only one port, so which is less than or equal to itself. So by default is a total order. Okay, so let's introduce some special elements in Hasse diagrams. Which can be translated by special elements in posets. Hasse diagram is so powerful that we can try to build a theory of order sets by simply doing Hasse diagrams, abstract Hasse diagrams, without further, specification of the nature of those elements, just diagrams. Okay, so we discuss interchangeably Hasse diagrams and posets. So let's say x with less than or equal with a partial order relation is a poset. So let's define a couple of concepts. Small a belonging to big X is a minimal element. If in the Hasse diagram, minimal element is there is nothing below. Nothing below A in the Hasse diagram. How to put it in a quantifiable formula? So in other words, for every X, if X is less than or equal to A, then X equals to A. So the only element in the Hasse diagram which is below A, which is less than or equal to A, is only A. So in other words, A is at the bottom, at the real bottom. But be careful here. The Hasse diagram has more than one bottom, and also more than one top. So, what about the maximal element? A belonging to the poset X is a maximal element if nothing above it. So nothing above A. Nothing above A in the Hasse diagram. We're using a formula for every X. If A is less than or equal to X, so if X is hypothetically A or above A, then the only possibility is X to be A. So that means A is a maximal element, nothing above. So here is a quick diagram which will help you understand the concept. So this is a Hasse diagram. Let's give some names here: A, B, C, D, E, A. If you look at this diagram, nothing below. So minimal elements are A and B. Maximal element means nothing above. Just sky is the limit. So above E, nothing. Above F, nothing. We cannot climb further if we are at E. We cannot climb further if we are at F. So maximal elements in the poset are E and F. Okay, so what about very related but actually different concepts are least element, greatest element. But okay, before going to greatest least element, let's try to prove you what. Let's mention a theorem here. Every finite poset or every finite Hasse diagram is minimal and maximal elements. Every finite poset has the Hasse diagram is minimal slash maximal elements. No matter what, as long as it is finite, it has minimal and maximal elements. Let's do a sketch of the proof, something like this. How to prove that a finite poset slash Hasse diagram has minimal and maximal elements. Let's go. Let's prove that it has maximal elements. So let's assume that we have an element A in a set. Let's assume that A is not maximal. Let's call it A1. A1 is not, so A equals to A1, not maximal. If it's not maximal, just pick one or the other. If it's not maximal, well, if it is maximal, we are done. So the theorem is proved. If it's not maximal, we can climb further from A1 to A2. If A2 is maximal, we are done. If not, we can climb from A2 to another A3. If A3 is maximal, we are done, because we proved that it is maximal elements. If not, climb again, A4. In which case, we don't have maximal elements. We can always climb. That contradicts the finite character of the set. If we can continuously climb, then the set is infinite, which contradicts the assumption. So no matter what, the process of going up continuously must stop at some moment, because otherwise the set will be infinite. So every finite poset or every finite Hasse diagram has minimal and maximal elements as well. But if we remove the condition that poset is finite, then there's not true. So because we can look at the integers, V with the usual order is an order set. What's the Hasse diagram of it? Well, it's infinite Hasse diagram, 0, 1, 2, 3, forever, goes up forever. Then we get -1, -2, -3, and goes down forever. So the set of integers with a regular usual order among integers does not have minimal, does not have maximal elements. Okay. This being said, let's discuss a related concept, but different from minimal maximal, least slash greatest. Least slash greatest elements in posets slash Hasse diagrams. So a least element. So A belonging to X is a least element of a partially ordered set X with an order relation less than or equal. So what does it mean? In the diagram we can climb from A everywhere we want. So let me give an example. So this has a diagram. The element here is the bottom. This, of course, this minimal. Of course, it's minimal because it's nothing below. But it's more than minimal. It's even so. There's more. Being minimal is dwarfed by the fact of being least element. We can do better. Better yet. It's a least element. Before starting from this element, name a point of the diagram. Let's say this one. I can climb from this element to this one. So I can go like this, continuously climbing like this, like this, like this. I can climb the diagram from a list element everywhere else. We can climb everywhere else. So this is a minimal element, but even better than minimal element is a list element. So basically, it's a logical consequence is that list element, any list element is minimal element. Any list element is minimal. Not every minimal is a list element. Not every minimal element is a list element. Even more so, if we have two or more minimal elements, then there is no list element. So that's an important text here. Any list element is minimal. Not every minimal element is a list element. Right. So like in this case we have two minimal elements, none of them is a list element. But if there are two or more minimal slash maximal elements, then there is no list slash greatest element. So if there are two or more minimal slash maximal elements, then there is no least slash greatest element. In the sense that we read the first ones together and the second ones together. So if there are two or more minimal elements, then there is no least element. If there are two or more maximal elements, then there is no greatest element. Let's see, let me rephrase this for maximal. Any greatest element is maximal. And not every maximal element is the greatest element. And like we said before, if there are two or more maximal elements, then there is no greatest element. How we just gave a quantified description of a least element. How to find the write down the definition of a greatest element? So B belonging to X is a greatest element of the partial set X with a recall if what? We can climb from wherever we start, we can climb to B. If for every X does not equal to B. So that means in the Hasse diagram, no matter where we start, we can climb to the maximum element square is B. So I can start here, just climb here. We can start here, just climb continuously to B. So no matter where we start in the Hasse diagram, we are either at B or we can climb continuously to B. That means B is the greatest element. Okay, I use the term the greatest element, but this needs a little bit of explanation. So this kind of follows from the two important, which are dual to each other, theorems. So if a least element exists, then it is unique. So theory. How to prove it? So we'll prove it by saying that assume there are two elements that qualify for the title of least element, and then we show that they are equal. So say both A and B qualify as least element. So what does it mean? Let's write down that A is the least element. For every x, A is less or equal to x. Right. So because that's what I mean, x, A is the least element. Because I can climb in the diagram to any element x starting from A, climb continuously. So that means A is the least element. Then we'll check this one. B is also a least element. B also qualifies a least element for A or for all x. B is less than or equal to x. Let's get some names here. Numbers. There's 1, there's 2. So now that we got those things, there's a quantifier here. So from 1, what does it follow? If A is less than or equal to x, no matter what x, it follows that for the special case when x is b, it follows A less than or equal to b. Right. Let's universal instantiation. Right. From 2, it follows. So since b is less than or equal to x, no matter what x is, b is less than or equal to a. Now, we got those two things, a less than or equal to b and b less than or equal to a. From these two things, via antisymmetry, what are the antisymmetric characters of the relation? For every x and every y, if x are y and y are x, then x equals to y. So if a less than or equal to b and b less than or equal to a, then a equals to b. So we just proved that if a and b both qualify as a least element, then they must be equal. And hence a least element, if it exists, is unique. Of course, if possible, the least element doesn't exist, right? So it's possible that no least element exists and no greatest element exists. And this is a nice example of Hasse diagram without least element, without greatest element, like a Feynman diagram.